Welcome to Lecture 4.1, Eigenvalues and Eigenvectors. This is a topic that I expect most of you have already seen from your introductory linear algebra course, but I will not assume that. I even mentioned them at the very end of my lecture 3.7 on tensor products. I use it to motivate another example of how tensor products arise behind the scenes. Let's get started. Throughout, we will assume that A is an n by n matrix over a field K. So it represents an endomorphism of a vector space isomorphic to K to the n. Remember, endomorphism just means a linear map from X to itself. We will assume that K is algebraically closed, which means that every non-constant polynomial has a root. The most common algebraically closed field is the complex numbers. And by common, I just mean based on what most people are familiar with. Nothing technical about that definition. So let's do some non-examples. The rationals. This is not algebraically closed because x squared minus 2 has roots plus or minus root 2, which are not in Q. The real numbers. Not algebraically closed because x squared plus 1 is a polynomial over R that has roots plus or minus I, which are not in R. And there's many fields between these and bigger than R, which are not algebraically closed as well. So to get something closed, we basically have to throw in all of the roots of polynomials over these lower fields. And if we do that, we get the complex numbers, C. Now, there's other ways to construct this. For example, C is just equal to R adjoined I, which means the set of all A plus BI, where A and B are real numbers. So you really only have to include I if you're doing what's called a field extension, or a join I. But that said, C is still is going to contain all of the roots of polynomials over these lower fields. So for example, if we have a polynomial, let's say an x to the n plus a1x plus a naught with complex coefficients, then let me call this f of x. Then f of x is going to have a root. Let's call that root r1. So that means that we can write it as x minus r1, and we can factor that out times some g of x. And this is going to have degree n, and this is going to have degree n minus 1. So now we can find a root of g and write this as x minus r1 times x minus r2 times, let me say, h of x, and so forth. You can finally factor out all the roots and write f as x minus r1 times x minus r2 times x minus rn. So when I say up here it has a root, equivalently we could say has n roots, where n is the degree of the polynomial. And I should be careful. I guess I'm using n here and n up here. Those don't have to be the same. So this is actually a stronger thing, and I'm not saying these are distinct roots. They might not be distinct, but every polynomial factors completely. We say it splits over the complex numbers. Now, there are other algebraically closed fields. Let me do another non-example. I'll do this one in red. If you take the field F2 or Z2, which is 0, 1, then x squared plus x plus 1 does not have a root. You can just check 0 and 1 are not roots. So what you could do is you can do a field extension. This is going to have a root in a larger field. And it's not clear at all how to construct that larger field. It's not really a topic for our class. But no matter how large of a finite field you have, there's a field of size 256, 2 to the 8, which is f 256. For every prime power, there's unique finite field of that size, which is abstract, and it involves a quotient space of polynomials. It's not a field of numbers, but you can always find polynomials that have roots that don't have a root in that field. So sort of like how you start with Q and just throw in all of the possible roots and keep doing that, and you eventually get the complex numbers. This is called the algebraic closure, which we can always assume this exists because we can always just keep throwing things in. If there isn't a root, we can adjoin it. Finite fields have algebraic closures as well. So the algebraic closure of the finite fields of size 2 to the n is going to be an infinite field that has characteristic 2, which means 1 plus 1 equals 0. So think of it like mod 2. And for any prime, there's going to be an algebraically closed field like this as well. Now, these are hard to deal with. They're abstract. So this is what I mean when I say most algebraically closed fields, or the most common one is the complex numbers. So the reason this may seem like a strong assumption to assume we're over C, but I don't think it really is, because what we're basically saying is if you got a polynomial, you can always assume that it's got a root, because if it doesn't have a root, you can just go into a larger field where it does. So if you're working over the real numbers and you have an eigenvalue or you have a polynomial that has root I, just assume that it exists. Just go into the complex numbers. This leads us to our first definition, that if AV equals lambda V for some non-zero vector V and scalar lambda, then V is an eigenvector of A and lambda is an eigenvalue. We will often refer to V and lambda as an eigenvalue vector pair. Now, we may or may not put parentheses here or might put a hyphen here. But if we speak about eigenvalue vector pairs, that's what we mean, because every eigenvector has a corresponding eigenvalue. And every eigenvalue has at least one eigenvector. Let's note some basic results that you likely already know, that if A V equals lambda V, then A times C V equals C lambda V. So if we have an eigenvector V, the entire line spanned by V is an eigenvector. And sometimes we will see examples where we have a two-dimensional space of eigenvectors. So every eigenvector has an eigenvalue, but every eigenvalue is going to have at least a line's worth of eigenvectors, and maybe more. So it's worth talking about a geometric picture of this, how I like to think about these things, and how I think you should as well. So I've drawn this picture before. Suppose you pick a basis. You don't have to pick a basis, but I like to have in a grid. And we have, let's do 2 by 2 case. So this is E1 and this is E2, and this is R2. And we have the map A, then that's going to send this grid to some other grid. So maybe E1 gets mapped to AE1 here, and E2 gets mapped to AE2 here. I've done this picture before. I think you know where it's hard to draw, though. It's hard to draw accurately. So the idea here is, if you look at E1, E1 gets mapped up here. So E1 is going to rotate and stretch out to just somewhere up here. And E2 is going to rotate this direction and stretch out, I don't know, somewhere there. So claim is somewhere in between here, there's going to be some vector here that if you apply A to it, is just going to get scaled by A. And that's what an eigenvector is. You can think of it as, when you apply A, a vector generally gets twisted and rotated and stretched or scaled, maybe reflected as well. But an eigenvector is something that just, if you apply A to it, it just stretches it out. So it goes from here up to there maybe, or maybe here down to there, something like that. So it doesn't rotate at all. That's the mental picture that you should have. Now, it seems from this picture that no no matter where you put E1, put E2, that we should be able to find some sort, if you rotate it, you should be able to find some vector that seems like it seems like there should be a vector that's an eigenvector. It should stretch somehow. And that's going to be what we're going to prove next, that every matrix has an eigenvector. Now, it may not be in R2. Like, we know that a rotation, the linear map that rotates things 90 degrees is a linear map, but it's not going to, there's clearly no real eigenvector here, because if we rotate everything 90 degrees, nothing gets purely stretched. However, in that case, there will be eigenvectors over the complex numbers. Let's now prove that statement that I just mentioned. A has an eigenvector. This is actually quite easy. We will pick any, let's say, non-zero vector W in X. And we will consider the following n plus 1 vectors: W, AW, A squared W, all the way up to A the n W. Notice this is n plus 1 vectors, so they must be linearly dependent. That is the key there. So this means that there is some non-trivial linear combination of these vectors that is 0. So we can write, say, C naught W plus C1 AW plus C2 A squared W plus Cn A to the n W equals 0. Now we can factor out this W, so we can write this as C naught times, let's say, C naught plus C1A plus C2 A squared plus Cn A to the n W equals 0. Now, I've intentionally embedded a mistake in here to see if you would catch it. I want you to notice that we can't actually do this. C naught is a number, and A is a matrix. I can't add a number to a matrix. So what I actually have to do here is write C naught times I. And now I can add these up. And we're going to do this a lot. We're going to have polynomials that we'll be plugging in matrices. And what you can't do is, let's say, suppose you have a polynomial x squared plus 1, f of x. I can't just say f of a is a squared plus 1. I mean, that is not allowed, but what because you can't add a polynomial and a number, but what I can say is f of a equals a squared plus I. I guess I could have just put a hat on this. And you may say, well, it looks like I'm cheating. Where's the rigor there? I'm not going to get into it. Technically, it is because if we have the map of, let's say, polynomials over C, and we can also talk, so this is technically a ring, and we can also talk about the polynomials over a matrix A, and there is it's called a homomorphism between these two spaces that will send X to A, and it will also send the identity element, the multiplicative identity 1 to the multiplicative identity over here. So that's where this little voodoo comes up of not just sneaking this in here. But this thing here, I can write as, if you prefer, f, I guess I'll call it f. No, I'll call it p, because that's what we'll call this polynomial later. So this is p of a times w. This is a polynomial times w, and it's equal to 0. Now we can factor this polynomial. So let's say over here that p of, what variable should I use? I'll use t, I guess. So p of t, wherever the complex numbers factors completely. It is c naught plus c1 t plus cn t to the n, and we can write this as, let's write it as some constant times t minus lambda 1, t minus lambda 2 all the way up to t minus lambda n. So this thing is going to factor. And so this polynomial here we can factor. Imagine plugging a into here. We will get a minus lambda I, or a minus lambda 1 I times a minus lambda 2I, and so forth. So I will do that. So we can write this as c times a minus lambda 1I times a minus lambda 2I times a minus lambda n I w equals 0. So now we have a non-zero vector w. Maybe I should have said this before. A non-zero vector w times a linear map, which is 0. So notice that w is in the null space of P of A. So this map is not invertible. And this map also factors as a composition of these individual maps A minus lambda J I. So this is not invertible. So this is non-invertible because W is in the null space of P of A. So that means that thus sum A minus lambda J I is non-invertible. So we have a composition of n maps which is non-invertible. At least one of these maps must be non-invertible. Let's call it A minus lambda J I. So if this is non-invertible, that means, so then the dimension of the null space of A minus lambda Ji is at least 1. So pick any vector, let's call it Vj in the null space of A minus lambda Ji. Pick any non-zero, I should say non-zero, and that particular vector, see what that's, notice that that means that A minus lambda Ji times Vj equals 0, which is equivalent to A Vj equals lambda J Vj. So we have literally constructed an eigenvector for our linear map A. It's worth mentioning that a linear map, in this case A minus lambda I, is non-invertible if and only if its determinant is 0. In our setting, that means that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is 0. And the corresponding eigenvector is any vector that's non-zero in the null space. So in other words, we need this determinant to be 0 for there to be a non-zero vector in the eigenspace, and that's exactly what an eigenvector is. And so this is how we can characterize an eigenvalue. Any number that makes this determinant A minus lambda I 0. This is how we will actually find the eigenvalues and eigenvectors. And I'm going to do this for a 2x2 example. I'll do this fairly quickly because this is something that you have likely seen in your introductory course. So let's take a determinant of A minus lambda I for this case. So that is the determinant of 3 minus lambda, 2, 1, 4 minus lambda. So that is 3 minus lambda times 4 minus lambda minus 2. This is lambda squared minus 7 lambda. And then we have plus 10. So this is lambda minus 2 times lambda minus 5. So we have the two eigenvalues, and now let's find the eigenvectors. We'll start with, we'll call this one lambda 1 equals 2. So we need to find a vector in the null space of A minus 2i. So we need to find some v such that A minus 2i times v is 0. So let's write this down as a system. So if we plug lambda in For here, we get 1, 2, 1, 2 times, let's call it x1, x2 equals 0, 0. This is the system x1 plus 2x2 equals 0, and this tells us that x1 equals negative 2x2. And this means that our eigenvector, let's call it v1, is, well, let's be careful here. Whatever the heck x2 is, x1 is negative 2 times it. So if x2 is c, then x1 is negative 2c. So we can factor out a c, and we get negative 2, 1. So because eigenvectors, vectors are eigenvectors up to scalars, we usually just ignore the c and just write down, and we pick some value for c, say c equals 1, we get this thing right here. Let's do the same thing for lambda equals 5 now. So lambda 2 equals 5. So now we write a minus 5I times v equals 0. So that is now negative 2, 2, 1, negative 1 times x1, x2 equals 0, 0. As is always the case, this gives us two equations that are scalar multiples of each other. So we only need to write down one of them. x1 minus x2 equals 0. This one is easy. x1 equals x2. So our eigenvector v2 is c, or c times 1, 1. So here are our two eigenvectors. Let me just quickly draw that picture again with the grid that I like. So we can think about A as the linear map that sends so it sends E1 to the first column. So this is A E1. So to 3, 1, it sends it to there. And it sends E2 to the second column, A E2. So that is something like this. So this grid gets sent to this grid. So it gets reflected and warped like this. And it's saying that one of the eigenvectors is, so this vector right here, or this entire line, gets stretched by a factor of 5. So this vector here is going to get stretched way up here. And then the other eigenvector is negative 2, 1. That's going to be something like this. So this vector, so this corresponds to lambda equals 2, and this to lambda equals 5. So this linear transformation, while it's going to reflect and rotate this grid, this line here just gets scaled by a factor of 5, and this line gets scaled by a factor of 2. Let me finish by saying one more thing about this picture. So notice that these eigenvectors, let me call this one V1, that's this guy, and then this over here is V2. These are linearly independent. And it makes sense that they would be, because this line gets stretched by 5 and this one by 2. So there's really no way that you're going to have the same line get stretched by different amounts. So in this case, it's pretty clear that these are independent. And what's less clear is that if you have an n by n matrix and you have, say, 4 different eigenvalues, those are going to have 4 different eigenvectors. So it's not clear that one of them is not going to be a scalar of the other one, but perhaps there's some weird way for those things to only span a 3-dimensional vector space. But that is not the case, and that is what we will show in the next slide, that if we have distinct eigenvalues, the corresponding eigenvectors are independent. But before I go there, let me say one thing about this picture. So in this case, if we have distinct eigenvalues, we have distinct eigenvectors, and they form a basis for R2. So that means that if we take any vector x, we can write it as C1 V1 plus C2 V2. And it's very convenient to use our standard basis as a basis for R2. That's what we normally do, 1, 0, and 0, 1. But sometimes it's convenient to use a different basis. And a basis of eigenvectors is often a good one. And the reason why is because if we write A times X with this basis, then we get A times C1 V1 plus C2 V2, which is C1A V1 plus C2A V2, which is C1 lambda 1 V1 plus C2 lambda 2 V2. Now, why is this so helpful? Well, imagine that we want, instead of compute AX, we want to compute A to the 1,000th, or A to the power of 1,000 times X. Now, we would normally have to do matrix multiplication 1,000 times, which is computationally difficult. I guess it's not bad for 2 by 2, but it's still undesirable. And if we get into large matrices, it quickly becomes prohibited, especially if we want maybe 1,000,000 instead of 1,000. But notice that we can just, what we can do instead is just, if we put 1,000 here and we put 1,000 right here, now all that happens is we just raise these eigenvalues to power 1,000 individually. So it's really easy to compute. In this case, it's C1 times 2 to this 1,000 times V1 plus C2 5 to the 1,000 power times V2. In other words, it's really easy to compute exponents of numbers compared to matrices. This is something we can do immediately, whereas matrix multiplication is more complicated. So this is one reason why an eigenvector basis is very nice. A lot of times in applied math, maybe like in like a population matrix, we want to compute what the population is going to be 1,000 iterations down the line, and we might need to compute something like this. And this also makes it clear that if we want to say something like, what's the limit as n goes to infinity of a to the n times x, what that's going to be. Like here, it's obviously going to go to infinity, well, it's going to blow up. But something else that's clear is that this term is going to dominate because 5 to the 1,000 is much bigger than 2 to the 1,000. So asymptotically, this term is going to win out. And maybe it's more clear if these were negative eigenvalues and they're going to go to 0, we can see which one goes to 0 faster than the other one. So it's very convenient to have a basis of eigenvectors. As we will see, we won't always have a full set of eigenvectors, but later in this series of lectures, we will see how we can make up for that by what's called generalized eigenvectors. And we will always have a full set of generalized eigenvectors. Okay, so let's go back to that question about how to show that if we have distinct eigenvalues, then the corresponding eigenvectors form a linearly independent set. Here is that statement formally. Eigenvectors of A corresponding to distinct eigenvalues are linearly independent. So in other words, if we have lambda 1 up to lambda, let's say, k are distinct with eigenvectors v1 up to vk. So let's suppose that this is false. Let's suppose that we have a linear combination of eigenvectors which is 0. So let's say that c1 v1 plus cm vm is equal to 0, and let's assume that m is minimal such, or with respect to the fact that all ci's are non-zero, because we know that there's at least one of these, or at least two of these are going to be non-zero. So we might as well assume they are all non-zero. Otherwise, we can just ignore those particular eigenvectors. And let's let m be the minimal such linear combination. So what we will do is we will show that we'll contradict minimality by coming up with a linear combination that has fewer terms. So the first thing we're going to do with this, well, there's two things we're going to do with this. The first thing is multiply by a. So let's take a times c1 v1 plus cm vm, which is going to be 0. And this is also going to be c1 lambda 1 v1 plus Cm lambda m v. Actually, I'm going to say Cm minus 1 lambda m minus 1 v plus Cm lambda m v. You'll see why in a second. So the first thing I do here is I multiply by a. The next thing I'm going to do is I'm going to instead multiply this by lambda j. So instead of multiplying this by a matrix, I'm going to multiply it by a number, namely lambda j. And if I do that, then I get C1 lambda m. Did I say lambda j? Lambda m. C1 lambda m v1 plus Cm minus 1 lambda m v. I forgot my Vm minus 1. This is Vm minus 1. And this is Vm plus Cm lambda m Vm. So this, of course, we know is 0. And so let's subtract this. So let's now subtract this second thing from the first one. And what we get is we get C1 times lambda 1 minus lambda m times V1 plus Cm minus 1 lambda m minus 1 minus lambda m times Vm minus 1. And notice that these two things right here cancel each other out. So now we have a smaller linear combination. By smaller, I mean with m minus 1 terms. That is 0. And notice that all of these coefficients are non-zero because the CIs are non-zero. And the eigenvalues being distinct means that all of these differences are going to be non-zero as well. So we conclude, let's say this contradicts the minimality of m. Now, if you look at any book, you're typically going to see the same proof, but you're going to see it in summation notation. And I think I've said this before. So, you have CI VI from I equals 1 up to n equals 0. And for whatever reason, I find this psychologically easier to deal with than this summation notation. And maybe it is just psychological, but that's why I spend a little more time, a little more space to write it out like this than I do with this. Let's continue with the theme of x having a basis of eigenvectors of A. In this case, I claim that A is similar to a diagonal matrix. Recall what that means. That means that A equals P, D, P inverse, where D is diagonal and P is invertible. In this case, we say that A is diagonalizable. So I will verify this by actually showing you how to construct such a P and a D. Now this is a good time, if you have not already, go back and watch my video on change of basis matrices. So I'll assume that that's something that you have learned if you haven't watched it. And remember that if A is a matrix, we can assume it's a linear map from A to A with respect to a basis. I called it our old basis, E1 up to En. If we want to change a basis, then what we do is we take a matrix P or we construct a matrix P by putting our new basis in the columns. And then that is a isomorphism from X to itself. And then the matrix, which is PA P inverse. So that means, well, first if we read right to left, it's P A P inverse, that matrix is going to be the matrix with respect to our new basis, V1 up to Vn. And I claim that this matrix is diagonal. And let's think about why this is. So first of all, I'm talking about the same linear map with two different bases. So I'm going to actually speak of that linear map as T, just so we don't confuse it with the matrices A and D. So if T is a linear map, so I claim that D is going to be the matrix of the diagonal matrix with eigenvalues lambda 1 up to lambda n on the diagonal. And let's think about why that is. So remember how to construct such a matrix with respect to this basis, this so-called new basis. Well, we take our input basis, which is V1 up to Vn, and we apply T to that, and we write this as a linear combination of our output basis, which is also, in this case, the VIs. So TV1 is lambda 1 V1 plus 0 V2 plus etc. TV2 is 0 V1 plus lambda 2 V2 plus so forth. And TVN is 0 V1 plus 0 V2 plus all the way up to lambda n Vn. And these are the columns of the matrix. And you can see that this is going to be a diagonal matrix, D. And so that's exactly what this matrix is. So I've shown you why how this matrix, which is we know is reading right to left, PA, P inverse, is just a diagonal matrix. So this is intuitively why it should be true using the commutative diagram that I did previously in the change of basis lecture and how to construct a matrix with respect to a different basis. But let's actually verify this a third way, algebraically. So let's verify why dP is equal to PA, or I should say reading right to left, that is why. So let me write this down. So let's check why doing D and then P, which is really PD, why that is equal to AP, doing P and then A. So let's start with AP. So AP is A times V1 up to Vn. Remember, that's what P is. It's the matrix of the eigenvectors. So we can move A inside, and these guys are column vectors. So this is A times V1 up to A times Vn. And now since these are eigenvectors, I can write this as lambda 1 V1 up to lambda n Vn. And now remember what these eigenvectors are. So these vectors are the columns of P. And the columns of a matrix is just the image of the standard unit basis vector. So this one is A times E1, and this is A times En. So I can write this as lambda 1 times PE1, lambda n PEN. Now I can pull the P out, so I can write this as P times lambda 1 E1 up to lambda n En. And now notice what we have here. This thing here is just the diagonal matrix, lambda 1 up to lambda n, which is, so this is D, so this is PD. And we have indeed verified that A times P is P times D. In other words, doing P then A is the same as doing D and then doing P. So here are three ways to think about why this is true. So henceforth, when you hear that something is diagonalizable, rather than thinking of this as being similar to a diagonal matrix, I think a better way to think about this is that there is a basis of eigenvectors. So think of this in a basis-free way, that we can find such a basis consisting of eigenvectors of the linear map. And I think we're going to leave it there. Stick around next time for the characteristic polynomial and the Cayley-Hamilton theorem.